Before starting, put the auto-generated YouTube subtitles in French or your mother tongue to get everything, and slow down or speed up the pace as needed. If you don't have time to watch it, just listen this video as a podcast while doing something else. Now listen and learn English as exploring our world. What came before everything? It's a question that's haunted the human imagination ever since we first stared up at the stars and wondered about our place in the cosmos. To really begin our exploration, we first need to set some common ground and get clear on what the Big Bang Theory actually describes, and what it doesn't. To venture into the before, we really need to have a crystal clear understanding of the event itself, the Big Bang. If we trace the expanding universe back in time, all the matter and energy we can observe today converges into a single point. So what happened immediately after this singular moment? The period just after the Big Bang, known as the Planck epoch, lasted for an infinitesimally small fraction of a second. When we ask, what came before the Big Bang, we fall into a trap woven into our language. Our minds expect a before, but if time itself began with the Big Bang, the question becomes a paradox. Maybe there was no before, just the event that gave rise to time itself. To understand, we must rethink our assumptions about reality. Albert Einstein revolutionized our understanding of gravity, space, and time with his theory of general relativity. Space and time are dynamically linked in a four-dimensional continuum known as space-time. Massive objects warp the fabric of space-time, affecting motion and time flow. Time is relative. It runs slower near massive bodies. The Big Bang Theory describes a singularity where space-time begins. To grasp a beginning without a before, Stephen Hawking used a powerful analogy. Imagine standing at the North Pole. There's no north of the North Pole. Likewise, asking what came before the Big Bang is like asking what's north of the North Pole. Time begins at the Big Bang. Before that, the question simply doesn't make sense. The universe is a self-contained system. No edge, no before. When general relativity meets quantum mechanics, certainty dissolves. The universe's beginning blurs from a sharp point into a haze of probabilities, where space, time, and nothingness lose meaning. Instead of a definite start, quantum physics suggests our universe could have emerged from a fuzzy, probabilistic state, abiding by the strange laws of the quantum realm. In our everyday experience, nothing means the absence of everything, no matter, no energy. But in quantum physics, this concept of nothing does not exist. The quantum vacuum is a dynamic landscape where particles are created and destroyed. This idea stems from the Heisenberg uncertainty principle. Energy fluctuations can create virtual particles, which then annihilate each other. The Casimir effect proves the quantum vacuum exerts physical force. Perhaps the universe arose from a massive quantum fluctuation, igniting the Big Bang. Imagine our universe as a random fluctuation in a quantum vacuum. No grand purpose, just a cosmic accident. By sheer chance, a massive energy surge could create a bubble, an unstable high-energy state. This bubble rapidly expands, kickstarting the Big Bang and filling the universe with energy and matter. Remarkably, the universe's total energy could be zero, making existence the ultimate free lunch. The idea that our universe was born from a quantum fluctuation suggests it may not be unique. Instead, we could be one bubble in a vast multiverse, each universe with its own laws. Our universe, with its perfect conditions for life, might simply be one of the lucky ones in a cosmic lottery. Eternal inflation is the engine behind the multiverse theory. It suggests that while our universe began with a Big Bang, the cosmic fabric keeps inflating, endlessly spawning bubble universes like ours. Each bubble is a new universe, forever separated from the others, an isolated island in a vast cosmic sea. Beyond the chaotic froth of the multiverse, there's a theory of a single universe in an endless loop of birth, death, and rebirth. This is the cyclic universe model, proposing our Big Bang is just the latest in an eternal succession. The universe bounces, triggering a new Big Bang, starting the cycle anew. It reimagines the cosmos as a circle with no true beginning or end, a self-sustaining eternal cosmos requiring no external creator. While the idea of a cyclical universe is, really elegant, it still has to stand up to scientific scrutiny. If our universe was born from the collapse of a previous one, could there be any lingering evidence, any faint echoes of the cosmos that came before? Well, proponents of these theories believe the answer is yes. The transition phase of the Big Bounce, while incredibly violent and hot, might not have been hot enough to completely erase all information from the prior epoch. Some large-scale structures or patterns from the preceding universe might have survived the fiery rebirth, leaving a subtle imprint on our own cosmos that we could potentially detect today. One of the most promising places to look for such evidence is in the cosmic microwave background, or CMB, the faint afterglow of our own Big Bang. The standard inflationary model predicts that the CMB should be almost perfectly uniform, with random Gaussian fluctuations. But some cyclic models predict specific non-random patterns or anomalies in the CMB's temperature variations. For example, some theories suggest that a previous universe's gravitational waves, or large-scale structures, could have imprinted themselves onto the initial conditions of our universe, creating subtle cold or hot spots in the CMB that would be difficult to explain with standard inflation alone. Scientists are meticulously scanning the CMB data from probes like Planck for these very signatures. They search for concentric circles of low-temperature variance, which could be the fossilized remnants of black hole collisions from the previous eon. Another potential clue could be found in the large-scale distribution of galaxies. The way galaxies are clustered across the universe might actually retain a memory of the structure of the cosmos before the last bounce. Finding such a preferred axis or an unusually large-scale pattern in the cosmic web would be a monumental discovery, offering a tantalizing glimpse into the universe that existed before our own. To date, no definitive evidence for a cyclic universe has been found. The CMB appears to be remarkably consistent with the predictions of the standard inflationary model. But, the search is far from over. The signals from a previous eon are expected to be incredibly faint and difficult to distinguish from random noise. As our technology improves and our understanding of these models becomes more refined, we may yet uncover the telltale signs of a past existence. The prospect of finding empirical proof of a universe before our own remains one of the most exciting frontiers in modern cosmology, a genuine ghost hunt on a cosmic scale. What if the universe didn't need a bounce or a preceding cycle? What if, actually, the problem lies in our very insistence on a beginning? This is the foundation of one of the most elegant and, honestly, mind-bending ideas in cosmology, the no-boundary proposal, developed by Stephen Hawking and his collaborator James Hartle. This theory tries to resolve the issue of the Big Bang singularity by applying quantum mechanics to the universe's origin in a really unique way. It suggests that if we go back in time, the distinction between time and space just dissolves, and the universe's origin point isn't a sharp, singular beginning, but rather a smooth, rounded-off cap. To get a sense of this, let's return to the analogy of the Earth's surface. The North Pole is a specific point, but there's no edge or boundary there. It's just another point on a curved surface. The no-boundary proposal suggests that the universe's origin is similar. As we approach the Big Bang, time as we know it, this forward-marching dimension, begins to behave more like a dimension of space. The 3 dimensions of space and the 1 dimension of time merge into a 4-dimensional, purely spatial geometry. In this state, there's no before because the concept of time has been replaced by another dimension of space. This quantum state is likened to the South Pole of the Earth. Just as the South Pole is the southernmost point, the beginning of the universe is a point where the nascent cosmos is fully self-contained. It has a finite size but no boundary, no edge, and no starting point in time to precede it. The universe didn't appear at a certain moment, it simply is, with its history described by a closed, curved surface in 4-dimensional space. The laws of nature themselves are sufficient to describe a universe that simply exists, without any need for a cause or a moment of creation. It is a universe that is completely self-contained. The no-boundary proposal is a profound philosophical and scientific statement. It suggests that asking what came before the Big Bang is ultimately a meaningless question. Not because time started there, but because the very nature of time changes so fundamentally that the concept of before dissolves. The universe would have no beginning in the traditional sense, no moment of creation out of nothing. It would simply be a timeless, spaceless quantum geometry from which space-time as we know it emerged. While highly speculative and, mathematically complex, this theory offers a compelling vision of a universe that requires no explanation beyond its own existence, a complete and beautiful cosmic system. Long before science, humans gazed at the stars and wondered, where did all of this come from? Across cultures, creation myths offered answers, stories of gods, cosmic eggs, and sung worlds. Today, science seeks our origins with new tools, but the question remains the same, connecting us to ancestors who also looked up in wonder. Why is there something rather than nothing? This question, posed by Leibniz, is perhaps the deepest mystery of all. Science suggests the universe exists because the laws of physics allow it. Others see purpose, a creator willing the universe into being. Ultimately, this question invites us to reflect on our place in the cosmos and what it means to exist at all. So why does this question about a time before time truly matter? We may never find a definitive, testable answer. The nature of the problem, lying at the very edge of observable reality, might mean that our theories about a pre-Big Bang era will forever remain speculative. However, the value of the question is not solely in finding the answer. Its true importance lies in the act of asking it. This single, seemingly unanswerable question has been one of the most powerful engines of scientific progress in human history. It relentlessly pushes us to challenge our assumptions, refine our theories, and invent new ways of looking at the universe. The pursuit of this mystery forces us to confront the biggest gaps in our knowledge. It is the friction between general relativity and quantum mechanics at the singularity that drives the search for a unified theory of quantum gravity, the holy grail of modern physics. It is the fine-tuning problem that gives rise to radical ideas like the multiverse. Every attempt to solve the puzzle of our origins leads to deeper insights into the fundamental workings of reality. It expands our understanding of space, time, matter, and energy. The quest itself is a catalyst for discovery, sparking innovation in both theoretical physics and observational cosmology. Beyond the realm of science, this question matters because it shapes our perspective of ourselves. Contemplating the origin of everything invites a sense of humility and wonder. It connects us to the grand cosmic story, reminding us that we are part of something unimaginably vast and ancient. It encourages us to think beyond our daily concerns and to appreciate the incredible improbability of our own existence. To be a conscious being, capable of asking these questions on a small planet orbiting an average star, is a remarkable thing. This sense of awe can be a powerful source of inspiration, art, and a shared sense of human identity. Perhaps the real answer, then, lies not in what came before, but in what we do now. Our quest to understand the universe is a reflection of our most noble qualities, our insatiable curiosity, our creativity, and our relentless drive to explore the unknown. Whether the universe began from a quantum fluctuation, a cosmic bounce, or something we cannot yet imagine, the fact that we can even contemplate the question is a testament to the power of the human mind. The search for our beginning is what propels us forward, ensuring that we continue to explore, to learn, and to grow. The question itself is the destination. Our journey to the edge of time has revealed mind-bending ideas, a universe born from quantum nothing, a cosmic foam of endless bubbles, and the serene, no-boundary proposal. Each theory offers a unique lens on our origins, reflecting humanity's timeless quest to answer, why is there something rather than nothing? The story of the cosmos is unfinished, its next chapter still waiting to be discovered. As we look up at the night sky, we're reminded of the vastness of the unknown and the wonder it inspires. The quest to understand what came before the Big Bang connects us to something larger than ourselves. It's a shared human journey, an invitation to stay curious, keep questioning, and never lose our sense of awe. For in asking these grand questions, we continue our incredible journey of discovery into the heart of the cosmos.